you'll have to do it simultaneously with me because again, it involves a lot of calculations and I can commit a mistake. Okay. So let us talk of solving Bessel's differential equation of order n. Okay. So that means my differential equation is going to be something like x square y double dash plus xy dash plus x square minus n square y equal to 0. This is the equation that we are going to solve now. Okay. Now, obviously the procedure remains the same here. We are going to have this equation rewritten in this form, plus x square minus n square by x square y equal to 0. So obviously x equal to 0 is a singular point, but I observe from here, if we compare with your standard equation, then your px is 1 and qx is x square minus n square. So as a result, your p naught is 1 and your q naught is minus n square. Okay, so therefore we are sure that x equal to 0 is a regular singular point for this equation. Okay, now the thing is, we have to solve it because it's a regular singular point. Therefore we have to use the Frobenius method to solve it. Now, to use the Frobenius method, we need to find the roots of the initial equation. And the initial equation in this case will be r into r minus 1 plus p naught r, that is plus 1 into r, plus q naught, which will be minus n square equal to 0. Is that okay? So what are the roots? The two roots for this. What do you get? Hmm?
Plus minus n.
Plus
So
n.
basically you are getting r square minus n square equal to 0, which gives r as plus minus n. Okay. So depending upon n, we have different cases, right? So if n is an integer, then the two roots are going to differ by an integer. Okay. So if n is a fractional number, then also the roots are going to differ by an integer. Okay. Or may not. Okay. So to solve that, let's see how the solution behaves later on. But since we have an n here, so I cannot write my y as the way we have been writing. So I'll assume y to be equal to, say, ck x to the power k plus r, because I have an n here, so this might create a confusion. So we'll let y be a solution because it's a Frobenius solution, so it's going to be of this form. Okay. So your y dash will be simply summation k plus r ck x to the power k plus r minus 1. Again, k from 0 to infinity. And your y double dash will be summation k plus r minus 1 ck x to the power k plus r minus 2. Again, k from 0 to infinity. Now substitute in your differential equation. So your differential equation was x square y double dash plus xy dash plus x square minus n square y equal to 0, right? So now when you substitute, it's going to be x square summation k plus r minus 1 ck x to the power k plus r minus 2, k from 0 to infinity, plus x summation k plus r ck x to the power k plus r minus 1. It's very similar to what we did the other day. Okay. And then you have x square minus n square y. So I'm going to get two terms here. So one will be plus x square summation ck x to the power k plus r, k from 0 to infinity, and the other is going to be minus n square summation k from 0 to infinity ck x to the power k plus r. Okay. Now we can simplify this further, and we observe that the first term will now be summation k from 0 to infinity k plus r minus 1 ck x to the power k plus r, right? Because this is x square, then you have x, and when you take that x inside that summation, you are going to get k plus r ck x to the power k plus r, k from 0 to infinity. The next one, the third one, which is x square into this, is going to be summation k from 0 to infinity ck x to the power k plus r plus 2, right? And it's going to be minus n square summation k from 0 to infinity ck x to the power k plus r equal to 0. Is this correct? Hope
Yes,
I'm,
ma'am.
Yes,
yeah.
ma'am.
Now we can combine x to the power k plus r. I have 1, 2, and 3 terms, right? So it's going to be, I think we can have ck x to the power k plus r common with summation k starting from 0 to infinity, and we are going to get k plus r into k plus r minus 1 plus k plus r minus n square, right? And the last summation is going to be summation ck x to the power k plus r plus 2 k from 0 to infinity equal to 0. Is that okay? Now see, these two terms can be simplified. You know, if you take k plus r common, then you are going to get k plus r minus 1 plus 1, right? So basically, this term is going to be summation ck x to the power k plus r into k plus r whole square minus n square, right? Is this clear? Right?
Yes, ma'am.
And the last summation, I can change the index and the starting point because I have to keep it as x to the power k plus r. So it's going to be plus summation k from 2 to infinity c k minus 2 x to the power k plus r equal to 0. I hope there's no confusion till this stage. Right? So, I mean, this is the same procedure that we have done earlier for so many problems. Okay. So now since this summation is starting from 2, so we have to consider the first two terms from here so that we can combine these summations. So when k is 0, it's c0 x to the power r into r square minus n square. And when k is 1, it's c1 x to the power r plus 1 into r plus 1 square minus n square, and the other terms I am now combining. So they are going to be x to the power, yeah, k plus r ck into k plus r whole square minus n square. I'm putting another bracket plus ck minus 2 equal to 0. Is that okay? I hope there's no confusion here. Hmm?
Yes, ma'am.
Now, now we equate the coefficients to 0. So from the first term, what we are going to get is C naught into R square minus N square is equal to 0. Now we have already concluded that R is plus minus N. So basically your R square is equal to N square. So from here we can, though we cannot draw any conclusion, but we are assuming that C naught is not equal to 0. Okay. But from the second expression, we are going to get C1 into R plus 1 whole square minus N square is equal to 0. Now, since R is equal to plus minus N, so that means this term will never be equal to 0. So that means the only possibility that we have is that my C1 must be 0. Okay. And from the last term on the left hand side, we are going to get our recurrence relation, which will give us that Ck is actually minus Ck minus 2 upon K plus R whole square minus N square. Is that so? Yeah, right. So this is going to be our recurrence relation that we are going to use. Okay. But one thing is very clear, that C1 is equal to 0. And this recurrence relation will hold good for every k more than or equal to 2. Okay. So from here, and because C1 is 0, so you can see from here, your C3 will be in terms of C1, your C5 will be in terms of C3. So basically, because C1 is 0, so your C1, C3, C5, C7. So basically, all your odd coefficients are going to be 0. And all your even coefficients would be in terms of C naught. Okay, so from here, now we have, see, we have this recurrence relation in terms of this. And we are going to get different values of these coefficients depending upon the values of R that we are using. Okay, so first of all, what we are going to do is we are going to consider the case when R is equal to plus N. Okay, so when R is equal to plus N, your Ck is going to be minus Ck minus 2 upon K plus N whole square minus N square. यही आएगा ना? Because your R is plus N, right? So can you simplify it? The denominator. So what do you get? Minus Ck minus 2 upon, क्या आ जाएगा?
K
K
square
square
plus 2kn.
plus KN.
K square plus 2kn, है ना? Which we can write as k into k plus 2n. Is that okay?
Yes, ma'am.
Yes, ma'am.
Right. So now, what will be C2? Now, C2 means when k is 2, right? So C2 will be, sorry, minus C naught upon 2 into 2 plus 2n, right? Which I think I can write as minus C naught upon 2 square into 1 plus n. लिख सकते हैं?
Yes,
Yes,
ma'am.
ma'am.
Right now, I'm not thinking of anything else except, till I get another terms. Okay. Now, what will be C4? C4 is going to be minus C2. Now, C4 means when K is 4, right? So it's going to be minus C2 upon 4 into 4 plus 2n, right? Which is actually nothing but plus C naught upon 2 square into 4 into 1 plus n into 4 plus 2n. यही आ रहा ना? Okay. Now, this I can also write as C naught upon 2 square into, I still write it as 4 into 1 plus n. And again, we can take 2 common, and I have 2 plus n inside the bracket if I take 2 common.
Yes, ma'am.
Right. Now see, okay, I have 2, which I'll retain as 2. I corresponding to this 2, I can say that I had a 1 here, right? Now this is 2 square, and 4 is also 2 square. So basically, I can write it as C naught upon 2 to the power 4 into, I'm writing it as 2 only as it is, into 1 plus n into 2 plus n. Is that okay? Now just compute C6. What is C6? What will be C6? Minus C4 upon, क्या हो जाएगा? 6 into 6 plus 2n, है ना? Which will be minus C naught upon, अब मैंने वहाँ क्या लिख दिया उसको? 2 to the power 4 into 2 into 6, right? अब उसका चल रहा है हमारे पास 1 plus n, 2 plus n. अब यहाँ से अगर हम 2 दोबारा से कॉमन ले लें तो आई कैन राइट इट एज 2 स्क्वायर इंटू 3 प्लस n.
Yes, ma'am.
Now, that means can I write it as minus C naught upon 2 to the power 6? Now I have a 6 here, right? Which is actually nothing but 3 factorial, right? And then I have 1 plus n, 2 plus n, 3 plus n. Without computing, can you write C8?
Yes, ma'am.
Now, will it be plus or minus?
Plus.
Plus. C naught upon, what will it be? 2 to the power
8. Then 4
8
factorial.
into 4 factorial into
Then 1 plus n,
1
2
plus
plus n,
n,
3 plus n.
2 plus n, 3
3
plus
plus n
n,
and 4
and 4 plus
plus
n,
n.
right? Similarly, C10 and so on and so forth. Now, if I have to generalize the formula, but definitely I am doing it for all even terms. So I will write the formula as C2M. Now, again, I have to use something else because I've already used N, I have already used K, I've already used R. So we are going to use M for the general notation of the recurrence relation. So what will be C2M equal to? Definitely minus 1 to the power something into C naught, right? What should be in the power? See, for C6 means 2 into 3, right? C8 means 2 into 4. For C6, it was minus. For C8, it was plus. So what should it be? Minus 1 to the power m
Yes, ma'am.
into C naught upon. Now, what will it be? 2 to the power
2m.
2m
2m.
into
M factorial.
m factorial into, starting with 1 plus n, 2 plus n, 3 plus n. Where will it end?
M plus n.
Yeah, m plus n. Okay? So this becomes the recurrence relation. In the case when r is equal to plus n. And basically, if you want your y1x, will be, now we'll take C naught common, right? And we'll have, because C naught is common everywhere, so 1 minus, it will be something like 1 minus, because C2 was minus, uh, x square, because C2 की term आएगी, upon 2 square into 2 factorial 1 plus n into 2 plus n. Then plus x to the power 4 upon 2 to the power 4. Sorry, it should be 1 factorial. I'm sorry. Into 2 factorial into 1 plus n, 2 plus n, 3 plus n, and so on and so forth. You get your series, the first linearly independent solution. Okay. Similarly, we'll now consider the case when r is equal to, now this is going to be my case 2 when r is equal to minus n. Okay. So when r is equal to minus n, your ck is going to be minus ck minus 2 upon, now r is minus n, so it will be k minus n whole square minus n square, right? So what would it be? Minus ck minus 2 upon, क्या हो जाएगा अब ये, k into
K minus 2n.
Minus 2n.
k minus 2n. So instead of plus, now you'll have a minus. Okay. Similarly, what will be C2 now? C2 will be minus C naught upon 2 into 2 minus 2n, which again we'll write as minus C naught upon 2 square into 1 minus n. So can you see the pattern now? Everything
Yes,
else
ma'am.
is
It's
the same, except that instead of 1 plus n, 2 plus n, and so on and so forth, we are going to have 1 minus n, 2 minus n, 3 minus n, and so on and so forth. Right? So can you write C2m directly now?
yes, ma'am.
This will be what? Minus 1 to the power m C naught upon, the other things will remain the same, 2 to the power 2m into m factorial. Now we're just going to have 1 minus n, 2 minus n, 3 minus n, and so on so forth till we have m minus n. Okay? And accordingly we can write our y2x. So y2x will be now, so basically your solutions, you see, your y1x is going to be x to the power n into some summation, and y2x is going to be x to the power minus n into some summation, and of course c naught outside. Okay, so you're going to have 1 minus, then plus, then minus. Similarly here also 1 minus, then plus, then minus, and so on so forth. So you're going to get your two linearly independent solutions, and your complete solution is going to be y1x plus y2x. Will you be able to complete now the fill in the blanks that I have left in between for you to do? Kar loge?
Yes, ma'am. Once show the previous slide, please.
Yeah, sure. Ye wali?
Yes, ma'am.
Yeah.
Thank you, ma'am. Done.
Okay. Now, the thing is that depending upon what equation do you have, like for example, question number 38, it says x square y double dash plus xy dash plus x square minus 1 by 4 equal to 0. Okay. So if you compare it with your general, Bessel's equation of order n, that means n is equal to n square is 1 by 4. Okay. So basically your n is plus minus half. So depending upon this, now you substitute the values there. जो हमने निकाले हुए हैं अपने, we have now y1x and we have y2x in terms of what? n only. Okay. So, or r, whatever you want to say. So basically n equal to plus minus half का मतलब हुआ कि basically your r is plus minus half. Okay, so in this case your y1 x is going to be x to the power half into, and again in the equation that you are getting you can substitute n equal to plus half there. Okay, and in y2x again you are going to get x to the power minus half, and then you can substitute n equal to plus half here, n equal to minus half here, and you will get the two solutions. Okay, so you don't have to solve them now because you have obtained a general solution. Similarly, if I change the term here, you can find, like you can try it yourself, try solving this also. Say x square y double dash plus xy dash plus x square minus 1 by 16 y equal to 0. Okay. Similarly, question number 39, it says x square y double dash plus xy dash plus x square minus 1y equal to 0. Okay. So just try these three yourself and you'll be able to do this. Okay. Is that okay?